Start the first lecture.
Okay, so I'm sorry that I didn't arrive when I was supposed to arrive yesterday. It was entirely my fault. I didn't read the schedule that Martin had created and properly enough to notice that I wasn't actually here on the first day. So I was asked to talk a little bit about the background to support the lectures made by the other people. I don't actually know much about transport theory myself. And I wrote out a grandiose list of all of the things I could possibly talk about and put them and sent them in. And it's already clear to me as I made my lectures up that I probably won't talk about all of them, but at least these are the things that I might give you an answer if you asked me about them. And so it doesn't make sense, I think, in 5 lectures to be very systematic and develop foundations of equilibrium, statistical mechanics, et cetera, from the ground up. More what I want to do is to talk about those basic objects that occur over and over again and which are useful in calculations. So, for example, today I'm going to talk about the Gaussian measure and the most important instances of it on the lattice and show why understanding of the Gaussian measure is useful for various examples. I'll use the Ising model as an example. Then if all of that goes according to schedule, next time I will try to go a little bit further. I'll be doing Feynman diagrams and a few other things connected with Gaussian measures today. I'm not really sure what my audience is here. If most of you are theoretical physicists, then basically what will happen to you is you will see translated into an unfamiliar language things you learned you might know already terribly well. If you're more from mathematics, then, well, the same thing will happen. But I'm coming from the mathematical side. I want to basically try to show that from the different sides of mathematics and physics, the same objects come up in interesting ways. And then, if all goes well, next lecture I'll be talking about well, supersymmetry a little bit as an interesting extension of the notion of Gaussian integration, because I think that'll play a role in some of the other lectures. Then I'll try to talk about the ideas of scaling in physics, illustrating them only with a hierarchical model. So that's the Wilson renormalization group and predictions that it makes for scaling limits. And that'll be certainly into the 3rd or the 4th lecture, and I'll then the other core topic that I might want to discuss a bit is called broken symmetry, and that actually is connected with phase transitions, which is what I'm actually supposed to be talking about. So let's talk about Gaussian measures first. So let's call this Gaussian measures on the lattice. So I'll draw a 2-dimensional lattice, but what we're doing is quite general for any dimension. And the lattice that we're interested in statistical mechanics, ZD, this would be Z2 here, integral coordinates, points with integer coordinates. And then actually, I just want to look at a finite subset, lambda in ZD. And to each point x in lambda, we have a variable phi sub x. Now, if you come from probability, you're used to the idea of using capital letters for random variables and small case letters for the values of random variables. And if you come from theoretical physics, you usually obfuscate the difference between those two things. And I'm afraid I'm going to do that. So when I wrote here a variable, well, I'm just suggesting that we're setting up a situation for doing integrals. But in fact, there are random variables, often denoted by the same letter in the background. So the collection of all of these random variables is just called phi. Sometimes I'll use the word field for that. It's a lattice field. And you want to build a Gaussian measure, you want a quadratic form on this. It's just a vector, really. So it's just a vector in, I'll write it as r to the lambda. So quadratic form, we need a matrix A. The rows and columns of this matrix are labeled by points x and y in the lattice. And then we can, I guess you can't see down here, so I'll go over here. Then we can make a quadratic form out of this matrix. Like this. And then if you take the case where the phi's are real, which is what I'll be doing today, but next time they might be complex, then this antisymmetric part of the matrix AXY drops out. So if you're interested in the quadratic form and you want to associate to a quadratic form in a unique way a matrix, you should take the matrix to be symmetric. Now, another thing you'd want to do is to make this quadratic form positive, because it's going to play the role of energy. So assume the eigenvectors of A are positive. Eigenvalues, thank you. I'll probably do that again. And actually it's equivalent to write this down. Phi A phi is greater than 0 for every phi which is not 0. And then we can make up our Gaussian measure. So e to the minus 1/2 phi A phi. We'll integrate over one copy of Lebesgue measure for every phi. So d lambda phi is my notation for product of d phi x, x in lambda. And we want to normalize the measure, which we can do because of this property here. So I'll put 1 upon n in it in front, so it's now a probability measure. And we'll call that probability measure d mu of phi. And just to be really confusing, instead of putting a subscript A on this matrix there to tell you what the Gaussian measure it is, I'll put a subscript C, and C is the inverse of A. So this is a most general Gaussian measure, basically, that you can write. In a moment, I'm going to get more specific and give you a kind of intuitive way of thinking about this. But before I do that, let's just list some famous properties that all Gaussian measures have. So first, it's easy to calculate their Laplace transform. So d mu c of phi, now the Laplace transform would be e to the minus, and I'll write it like this, phi comma f. I'm using the same notation for inner product as I am up here. Phi comma f is the sum over x in lambda of phi of x, f sub x, and these f's are just arbitrary parameters. They're dual. They're dual to the phi. And so what we're doing here is writing the Laplace transform of the Gaussian measure, and that you can compute it's e to the plus 1/2 f inner product with this c that I put here, f. Now, you get that, I'm not going to do it for you, but you get that by completing the square. So if you know how to do this in one dimension by completing the square, then you'll find that you can also do it in many dimensions by completing the square with a few matrices in it here and there. Now another property which actually comes from this one is that if you want to know what the second moment is, it's this matrix C, which is the inverse of that matrix xy. And so C actually stands for covariance. And it's better to label a Gaussian measure usually by its covariance than it is by the matrix that determines the quadratic form in it. Covariance has nice properties. Yeah.
Is phi x, phi y just the inner product, or you mean something?
It's just the inner product, phi x, phi, which, oh no, not this one, I'm sorry. This one is just, say, this is, takes some getting used to, this notation. I'm using x and y, which make you think of space-time points as labels, and phi is the value of some physical quantity at the space-time point x. And phi y is the value of the same physical quantity at the space-time point y. You could think of it as a displacement in a crystal. Then a third property, which is handy to, well, third thing that's handy to know, especially for next lecture, but maybe not for this one, is that you can compute this normalization, this capital N. It's, well, I probably have it wrong, but I mean, you can compute it. It's 2 pi to the, this notation, the absolute value on lambda, that means the cardinality of lambda, the number of points in lambda, times the determinant to the minus 1/2 of the matrix A. If you never did this computation before, you should ask...
Plus 1/2.
Plus 1/2, thank you, yes. Okay, that's already a typo in my notes. If you never did this computation before, it's really good fun. You should first try to decide that this is correct by taking the case where A is diagonal. And if you know how to do it for A is diagonal, then you can get it for A, an arbitrary symmetric matrix, because you can write a symmetric matrix as an orthogonal times a diagonal times an inverse orthogonal, and that's a change of variables. Then we come to the main example of this structure, which I'm going to call the lattice free field, and I'm not the only person who calls it that. So when you're giving examples of Gaussian measures, it's basically just a decision of what your C is, or perhaps what your A is. And to decide that, we're going to use the same discrete Laplacian, except it'll have its diagonal entries put back in, as was being discussed by Leonid in the last lecture. So, for example, let's consider something I'm going to write this way. You're going to try to interpret this, given what I already wrote, as an inner product of something with something else, and it actually is, but it's a different inner product slightly from the one I wrote above, and it's best to look at the right-hand side first. It's phi of x minus phi of y squared, and then you just sum over x, y, where xy is a nearest neighbor pair. And I'm going to make this a nearest neighbor pair, well, actually in the whole infinite lattice, said D, which immediately gives you a problem, because the way I've set things up, these variables phi sub x are only defined for this finite subset, so you have to worry about what's going on when you take a nearest neighbor pair like that. where one is outside and one is in. And what I'll do for that generally is to insist that the phi's that are outside are all set to 0. So there are different possibilities here, and these correspond to boundary conditions. So boundary conditions, phi x equals 0 if x is not in lambda. That's called Dirichlet boundary conditions. Because you should think of this as analogous to the integral of gradient phi squared, and that's called the Dirichlet form. And very commonly what you do is you set, very commonly you consider functions which vanish outside some domain, and then you are interested in the integral of over the gradient inside the domain. That's called Dirichlet. Of course, there are other possibilities which come up a lot. You could take your lambda to be a box-like region, and then you can identify these edges that go across the boundary. You can say that that's that one there. So this is periodic boundary conditions, and same way in the other direction. So there are these different things you can do. Is it the wrong way around? Well, I'm always totally confused about that myself. Okay, let me think about it. Okay, when you make A very, very big...
Usually we use N in front, then it's but if it's one away, it's one.
Oh, okay. So when you make A very, very big, I guess you make the measure very, very small, and that corresponds to N being very small. So, yes, that looks good. Okay, thanks. All right, now, it's okay to get that sign wrong. Sometimes.
Another thing about your conventions with pairs, you take x, y is equal to y, x? Or
yes, thank you. I'm going to be a bit sloppy on that here. Now, that's why I really want to put inverted commas here. Actually, x, I want to sum over, here I want to sum over x, y, and yx separately in this sum here. Yeah, I think I want to do that. In that case, I've got to put, wait a second, I have to be careful about this. Then I want to put a 1/2 in front. Yeah. Okay. Now, this thing is a quadratic form, and so it comes from a matrix. The matrix minus the Laplacian is such that, so it's again it's a matrix whose rows and columns x and y are labeled by points inside lambda, is such that this is the quadratic form for the matrix. So in other words, phi minus Laplacian phi should be this thing that I defined above, gradient phi, gradient phi. Now, that's the basic quadratic form, and then from that we can have two kinds of Gaussian measures. One is called the massive Gaussian, and this one is 1 over n, so this is d mu, is 1 over n e to the minus, and we take this gradient phi, and I'm afraid there's another factor of 1/2 besides the one I already put there. Minus, and we add in minus 1 m squared phi, So this is a parameter m greater than 0, which is called the mass. And so that's an important one. And then the other one is massless. And you just take m equals 0. But you have to be a bit careful with the massless one in the case of the periodic boundary conditions, which was one of the popular choices, because you can't normalize it. The capital N is infinite in the case of periodic boundary conditions. And one way to see that is to notice that in this formula here, if you were to change every phi to phi plus 1 million, this wouldn't know that. And so there's an overall translation that is not being weighted at all inside the Gaussian measure. And so you'll never be able to normalize the measure unless you do something when mass is 0. You see that otherwise you're okay in this case.
But boundary condition.
Yeah, the boundary condition. That's right. The boundary condition, if you have Dirichlet, is fine, but with periodic it isn't. So that actually leads to a couple of nice questions. Well, maybe I'll ask them in a second after I give my interpretation of this. Let's see. Just make sure I haven't forgotten anything yet. Let's give a mechanical interpretation for this Gaussian measure, just to make it more your friend. So one interpretation that I like is the bed spring. So this is the frame of your bed and the thing under your bed, okay, the springs. And you have springs. This plays the role of the Dirichlet boundary condition that sets the displacement of the spring equal to 0 at the boundary. And then you have all these springs in the middle. And actually, it's not strictly an example of what I've been talking about, because these displacements are vectors, right? But you could take the displacement in a fixed direction, say normal to the bed spring, and you could think of that as your phi of x. And so my first question for you is, which model is this, the massive or the massless, and why?
If that thing has a mass or not.
Well, this is the model. This is the physical model. Okay. So my question is, which of my two mathematical things is the correct description for this physical model? Massless, right? Massless. If you wanted to put in a mass, what that would mean is that you've attached your bed spring points to the floor by some additional springs. So if you think about that, then there are some fun things you can ask about. Like, for example, I've drawn a two-dimensional bed spring. Now, suppose it was an absolutely enormous bed, not just a king size, but an emperor-sized bed. What would it do in the middle? What would be? You see, you can ask what the variance of the middle displacement right at the center of the spring is a random variable with a distribution that you can get from this Gaussian measure. And you could ask, well, is that going to be a big variance or a small variance when the bed becomes huge? I'm not going to tell you the answer to that, but it's one of the questions that leads into some of the interesting things like broken symmetry and so on that come later. You can think about that. So, of course, if you find bed springs way too unserious, then you can talk about phonons inside crystals, which are just displacements of atoms in a crystal. So now let's look at why do I care so much about Gaussian measures? Well,
David?
Yes.
Maybe you could mention with the one-dimensional case too.
The one-dimensional case, yes.
That's the easiest one to understand. So.
Well, then the one-dimensional case. You mean this one?
The random walk, right? Basically.
The random walk, yes. Okay, that's a nice example. That's for sure a very good idea. So With random walk, you can start with a point which is where, well, phi is the name of the random walk. It's a bit strange, and in this case, phi sub x is time. 0, 1, 2, 3. In this, for random walk, what you want to do is to think of a lattice like this. It's only a half lattice. It's n, or a subset of n. And then at phi, at this place, phi sub 0, you just fix the position of the random walker to be 0. So there's an additional coordinate, which is the coordinate which I'm going to plot phi in. And then one step, this is his position at time 1, time 0, time 2. And the Gaussian field phi is a particular kind of random walk in one dimension in that case. It's a nice way to think about it. And if you do think about it, that gives you some insight into what's going on actually in some of these cases. Now,
yeah, it would be helpful if you mention the example of phonons.
yes.
Phonons, there is inertia. Inertia
Yes.
is important. And you solve this equation, you find normal modes. How is this related to this?
Well, I dare not go into that right now because it would be, I mean, it would sideline me a bit. I only wanted to.
This is just the potential energy.
Yeah, it's only the potential energy, right? I don't.
He's not
Okay.
talking about the
Okay.
kinetic energy.
Okay,
Yeah.
okay,
Mhm.
okay.
So let's take a look at the Ising model, which looks like a completely different model, because one of the themes that I want to get across is that these Gaussian measures are the basic approximation which you use in understanding all the other models of statistical mechanics. And irrespective of how much statistical mechanics you've had, I do hope that you've met the Ising model before. And what theoretical physicists do is they always write down the normalization of the measure rather than the measure itself. So I'm going to write that down for the Ising model. So there is a new variable, sigma. It's also associated to points in a lattice like this. But for the Ising model, sigma is only allowed to take on two values, +1 and -1, which you can think of as a little magnet pointing towards you or a little magnet pointing away from you. So sigma is, that's how I signal that it's going to have only the values -1 and 1. And then to signal that it can have each of these values as it pleases at every single lattice site, we'll raise that Cartesian product, if you like, to the power of lambda, meaning every lattice site, this sigma is -1 or 1. So sigma is a collection of spins. They're called spins. And then the typical kind of energy, potential energy, that you would like to give to these spins is of this form. There's some parameters called jxy. There's a whole matrix of them, coupling constants. And then there's sigma x, sigma y. And this is the sum again over all pairs, nearest neighbor, not nearest neighbor pairs, sorry. This is I should write it this way, x, comma, y in lambda. I want to sum over all of them. Now, the most common kind of Ising model that's studied is the special case where the j is 1 if x and y are nearest neighbors and 0 in all the other cases. But I'm doing something more general here. I'm allowing next to nearest neighbor interactions, if you like, or even more long-range interactions, just because we can. This is the normalization for a measure, which defines the probability distribution, which is the Ising model. And for some reason, physicists always write down the normalization rather than the measure itself. That's something you should get used to if you're in mathematics. And that reason is because from the normalization, if they're sufficiently clever, they can calculate all the correlations and other things by putting in extra variables and evaluating the normalization. So there's a lot of information in this thing, or there would be if I added some extra variables like a magnetic field. Now let's, I just want to do one thing here. I just
Put a
want to,
temperature in there, David?
well, that's in here.
Okay.
That's going to be in there. In a little while, I'm going to make a specific choice of this J. But we'll wait on that for a second. I just want to show you that you can rewrite this object in terms of a Gaussian integral. And it's very easy. This is an idea that goes back, well, it's been rediscovered by many people. It's Katz, in Mark Katz, Siegert, and then it's also called Stratonovich transformation. And the idea is that you look at this. So we'll need an assumption to make this work. But if you look at this, it looks like a quadratic form in sigma. And in particular, it looks like this when the F is the sigma. So that suggests that if the J is the right kind of a matrix to be a covariance, we can rewrite this whole thing here as we can say it's the Laplace transform of a Gaussian measure. So for that, we will need the Jxy. Again, you assume it's symmetric and positive eigenvalues.
The nearest neighbor Ising model isn't.
Which the nearest neighbor Ising model isn't. Exactly right, yes. That's why I wanted to do this case here first. Although there is something you can do with the nearest neighbor Ising model, it's not as simple as this. So here we go. We'll take this Z, and we've got this sum over the sigmas. And we've got this thing, but this thing is now going to be written using this formula backwards. So I'm going to write one of these down. D mu sub J, because J is playing the role of C, E to the minus inner product of phi, which is a new variable, which is what we're doing the Gaussian integral over. And instead of F, I have to write sigma, because sigma is playing the role of F. Now, what have we gained by that? Well, you can't see anything that you've gained until you move this integral past this sum. So let's do that. D mu J phi sum over sigma E to the minus phi inner product sigma. So let's stop here and look at that for a second. I claim this is a much simpler Ising model than the one you started with. The one you started with has what we call a two-body interaction. It's nonlinear in sigma. And the one you finished with here is linear in sigma. We're saying that you can write the Ising model as a kind of superposition over random fields. It's an annealed model in physics terms. You can write it as an integral over random fields phi of a Ising model, and this, if you know physics, is that plays the role of a magnetic field. But you don't have to know anything about physics. You just have to realize that this is incredibly simple to evaluate. And why is that? So you should look back into the notation what this phi sigma is. So what that phi sigma is a sum over points, x in lambda, of phi times sigma, like in that formula. And the sum, which is up in the exponent, I could take downstairs like this. And then it would just be phi x sigma x. Now, do anybody see why this is good? Well, even bolder, you can move the product past the sum and make it a single sum. So it's the same. it's the same as d mu j phi product over x, and it's really a one-site Ising model. There's a sum over a sigma at a single site of e to the minus phi x sigma. Now we can do that sum, and it'll give you something like a cosh. So we get product over x in lambda twice the cosh of phi sub x. Cosh, yes. And then, you know, physicists like to have things up in exponentials rather. They like to have exponentials of sums rather than products. So let's write this one step further as d mu j of phi e to the sum over x in lambda of the log of twice the cosh of phi of x. Now, let's make a particular choice of j to relate this to the massive Ising model that I was just talking about. At this point, in making this choice of j, I have to rely on things that I think Tom or someone else maybe is going to prove. There are properties of these covariances. C of xy is the inverse of m squared minus the Laplacian. And I want to take for my j I want to take it to be 1 minus the Laplacian xy inverse. What that means is take the inverse of the matrix and then take the xy entry. And I guess now I'm just going to state without justifying it that this kind of object, it's not nearest neighbor, but it's got exponential decay. As x and y get separated, the size of this matrix element goes down like the exponential of minus x minus y. So it's not nearest neighbor, but it's trying hard to be nearest neighbor. And then, you see, you can write this thing rather more explicitly as n inverse e to the minus 1/2 grad phi, my favorite quadratic form for the massless Gaussian. And then there's this business here, together with the 1, which I'm going to bundle into a thing called v of phi of x, which has to be summed over the lattice. And let's also put in a temperature at this point, because we want to know whether we're at low temperature or high temperature for this Ising model. So what I'll do is I'll put in a parameter beta, like that. So beta is the inverse temperature for the original Ising model. That's what it's called. If beta is large, there's a strong tendency for the spins to align, and if they're small, then they're quite disordered. And then that beta would come in like this. Beta inverse here. And there's a beta buried in here. I have to tell you what the v is. V of phi of x is 1/2 beta inverse phi of x squared with a minus sign in front of it. I'm sorry, I want to change this plus to a minus sign. Sorry about that. And then I want to change this to a plus, which is right. And then minus this log cosh business, log 2 cosh phi of x. And if we plot a graph of this v,
But shouldn't beta be also under cosh then?
I don't think the beta is under the cosh.
You just defined it in
Well, it's not that I just defined it. I really think it isn't there. If you just follow through this,
okay, you can always.
it's just not there. I mean, if you just follow the algebra, it isn't there. But if you plot this v, it looks like this. Well, depends what beta is, but for some values of beta, this is actually for a beta big. It looks like that. It's a double well thing. Now, I'm not going to carry this further at this stage, but the idea is that when beta is very, very large, what we have here is a massless Gaussian measure with a perturbation. It's called a perturbation. And the perturbation gives it a tendency for the spin, not the spin, this is phi, which is dual to the spin. The phi would like to be either around there or around there, because when beta is large, this is a huge double well like this. And that's a possible origin for a phase transition. It's not the usual way in which it's described with the Ising model, but it's a good way to do it because it's rather general. There are many, many models that come up as perturbations of grad phi squared, and then if you want some kind of fairly general way of approaching phase transitions, you can try to write your models as perturbations of Gaussians and start to ask if you can analyze them in these terms.
David, I have just a couple of comments.
Yeah.
The C up there, for those people who are taking notes, shouldn't that be an inverse on
That should be an inverse, thank you. Yes?
And then I guess maybe it's worth saying for beta small that the thing is convex.
That's right. Yes, very good point. Thanks. For beta small, it'll look more like that. It doesn't. I don't know that it goes through the origin, but it won't have two wells. So you can see a kind of way in which the model might behave radically different from small beta to large beta. Right, now, I know I have to rub something out, and I need an eraser. It looks like there's an infinite amount of blackboard when you start, but then you use up a lot of it very casually. Now, what's the point? I've just tried to describe, and I'll do some more of it next time, that models can be written as perturbations of Gaussians. You may regard this as a bit feeble because all I did was to write the normalizations of perturbation of a Gaussian, but that's not the whole story. You can write the model as a perturbation of a Gaussian or certain observables. So that suggests that you want a kind of science for analyzing perturbations of Gaussians. And that's called Feynman diagrams and Wick's theorem and things like that, and that's what I'm going to explain next. And for the theoretical physicists who are here, well, you can pull out your novels and read those. But for the others, this will be useful, I think. So let's talk first about Wick's theorem. So here it is. For P a polynomial in phi, you can evaluate the Gaussian integral of a polynomial by the following nice little formula. It's e to the 1/2. And now comes something that looks very like a Laplacian, but it's certainly not the Laplacian that I was defining just a moment ago. I'll tell you what it is in a second. Laplacian sub c, it depends on this covariance here. Acting on P, and then set phi equal to 0. What is this Laplacian C? It's a double differentiation of the form sum over x and y in lambda, put in your covariance cxy, differentiate with respect to phi sub x, differentiate with respect to phi sub y. And what do we mean by the exponential? We just mean expand it as a power series, which is going to be fine because these derivatives are acting on a polynomial, and pretty soon they run out of guys to differentiate, and so even though the series goes on forever, the contributions are only finitely many terms at the beginning. So e to the 1/2 Laplacian C is the sum 1 upon n factorial Laplacian C over 2 to the power of n. Now, if you're a probabilist, you've seen this formula before, but you didn't see it written this way. It's the formula for evaluating the moments of a Gaussian integral. which you've seen written as the sum over all possible pairings. But this is a nice way to write it. Now, once again, this being a kind of speedy, breezy course, I'm not going to prove it, but I'll just tell you what the idea is in case you want to figure it out for yourself or ask me afterwards. I need this eraser. I write it in this form, even though it's not standard in probability, because this is the best way to get into Feynman graphs. At least I think it's the best way. So the reason why this is true, proof hint, the Gaussian measure that's here, where do we see a Gaussian measure when we're doing ordinary analysis? We find it when we're solving heat equations, right? The fundamental solution to the heat equation is a Gaussian measure, and usually you're not doing it in quite such a grandiose context where there are a huge number of variables labeled by points in a lattice, but this is still the Laplacian acting on some finite dimensional real space. And so the hint is that you can solve d by dt of u equals Laplacian c of u by writing u is equal to p at time 0, by writing a fundamental solution. So it's a Gaussian convolved with u at time with p, or as e to the t over 2 Laplacian sub c acting on p, which clearly also solves this equation just by putting it in and checking. And so since you have two ways of solving the same equation, and since the solutions to the equation are unique, they must be equal. And if you think about that for a moment, out comes this. Now, let's do an example just to make sure we've got the right formula. So example 1, let's evaluate or see if we evaluate d mu c of phi a phi b. We know what this is. We know that this is the covariance. But we could check it by letting this thing act on the polynomial. As we're told to do. Now you have to remember that we're going to set the field equal to 0 after we've evaluated the derivatives. So when you expand this exponential out, in this sum here you'll get a first term which is n equals 0, which doesn't count because it doesn't do any differentiating, and so you're still left with a phi a, phi b, and then you set the phi a and the phi b equal to 0, so you get 0. Then you get a second term, which does count. So the second term in the exponential is this Laplacian c, 1/2 Laplacian c, acting on phi a, phi b. And then we can set phi equal to 0 at the end of that, but it won't matter because they both get differentiated. And then there's other terms which won't count because they get differentiated too many times. And then you evaluate this, so you look at the Laplacian sub c. This is just to make this formula your friend again. If you let this thing act on phi a, phi b here, then most of the sum drops out. X either has to be a or x has to be b, and then y has to be the other one. And there's a factor of 1/2 that I've put in front of here, which is good because that cancels out this choice about whether x is a or x is b. And then the Laplacian does its, the two derivatives annihilate these things and set x and y equal to a and b. So this is just CAB as it should be. Then I feel much better. Then we can do a much more interesting example, which brings in Feynman diagrams. You're standing up in a menacing
Be
way.
a device to assist you.
Oh, I see. I thought you were standing up because you were telling me my time. Oh, there are hooks, are there? Oh, okay.
You're at the end of the room, I think. It's something.
Ah, okay. Well, but I kind of like doing these big jumps and high kicks, and all kinds of bad tricks. Let's take this polynomial p to be phi a squared over 2 factorial phi b to the power of 4 over 4 factorial. Don't be too scared by the 2's factorials and 4 factorials. They're there for a reason, but we don't need to know what it is at the moment. So we want to evaluate the Gaussian integral of this particular 6th order. Plus or minuses? They're multiplied. They're multiplied together. It's a monomial. So I'm going to evaluate this thing by the same formula. Now this is a 6th order polynomial. So if you followed through this example here, you'll see that only the n equals 3 term counts in here. Now, Feynman diagrams are just simply a way of describing graphically all the different terms that can emerge by Leibniz's rule here.
But you have to divide by 3 factorial.
Oh, yes, I want a 1 over 3 factorial. Thank you very much. Yep. So let me just draw them, and then you will see what they mean, just from the drawing. There's a number here I'm going to put in a second. I'm going to tell you about that in a moment, but let's leave a space for it. And the other diagram, which describes the other way in which the derivatives can arrange themselves, looks like this. So these two diagrams, they're labeled graphs. The vertices, the vertices are labeled, but the edges are not. We'll come back to that in a second. But what you can see here is what this means is that one of these Laplacians decided to devote all of its love and attention to that one. So both legs, both the d by d phi's in one of the Laplacians hit that one. That's what that line means. Each line means a covariance. And the fact that this covariance begins at A and ends at A means CAA. So this is a factor of CAA here, this part of the diagram. This is a completely precise way, when I finished, of translating a diagram into a mathematical expression. And it's so precise that physicists, if you are coming from the other side of the divide here, physicists can actually do algebra extremely accurately and correctly, more so than you would be able to do just by doing the algebra, by using the diagrams. This one here, well, what do you think it is? It's the other two Laplacians in this formula, wherever it is. The other two Laplacians devoted all of their care and attention to a phi b to the fourth. That's the b. Sorry, this is the b here. So what does it mean? CBB, that's that one, and another CBB, that's that one. like that. Over here, CAB, that one, and another CAB. And then this one is CBB. And those are the kinds of terms that can arise by doing 3 Laplacians on that monomial. Now we want to know what the numbers are in front, and for that you have to lock yourself in a closet a bit, but I'll just tell you the recipe. What you do is this thing here, in physics terminology is called a tadpole, and for graph theorists it's a loop, which is really bad and really confusing because physicists have another use for loop. They mean a cycle. So that's a loop. That's a tadpole in physics terminology. That's the word I'm going to use from here on out because it's unambiguous. And for every tadpole, you put in a factor of a half. So I see here 1 tadpole, 2 tadpoles, 3 tadpoles, 1/2 cubed. Let me leave a bit more room here. Then another thing I see here is called an edge automorphism. You can flip that edge with that edge, and it's the same graph. And you put 1 over the order of the edge automorphisms in front. Over here, I see 1 tadpole, which is 1 factor of a half, and I see 1 edge automorphism, which is another factor of a half. And so that should be actually what you get. Let me just check and see that it is what I got. If you sit down and count the ways in which these particular diagrams can arise, taking into account, I'm taking into account, that's why I put these numbers here, so I could describe it to you in those terms. The factorials, the factorial that's in front of the Laplacian here is responsible for an action of the symmetric group on the edges, and that's why edge automorphisms somehow play a role here. Now, where's my eraser? So that's Feynman diagrams. Now we need to go on to another player in the land of Feynman diagrams, which are Wick powers. The reason why we need this is these tadpoles kind of clutter up the landscape a bit, and you can work with another class of, instead of working with monomials, you can work with a better class of polynomials, which, well, we will see that they're basically Hermite polynomials, which have orthogonality properties, and that helps in getting rid of some of these diagrams and making calculations easier. So let's take a look at those. This is the basic definition. Now, given that we're only defining Hermite polynomials in the end, as we will see, it's a little intimidating to see these things, but a colon on either side of a polynomial just simply means that you did the following operation. Well, actually, the colon has to be decorated by a C to tell you which covariance you're using. It meant that you did the following thing. E to the minus 1/2 Laplacian C acting on P. That's just notation for this thing. Now, that's to make you more comfortable with this, I just point out that it's a way of generating a polynomial out of a, for example, let's look at this case. Let's see what it gives us if we try. Okay, this is my choice of P, a 4th power of phi at the point A. So the recipe is a bit strange looking. Hit it with this e to the, notice this sign is the wrong sign in some sense. I mean, it's not the one you're used to, a minus sign there. Hit it with that and work out what you get. So there's a phi to the 4th here. And there's a 1, and there's a Laplacian sub c over 2 and there's a, with a minus sign in front of it, and there's a minus Laplacian sub c over 2 squared and a 1 over 2 factorial, all acting on that. Now, you're not setting phi equal to 0 at the end in this definition, so you have to evaluate all these terms, and you will get phi a to the 4th, I'm just going to copy them out, minus 1/2 4 times 3 CAA phi a squared plus 1/2 1/2 1/2 CAA squared times 4 factorial. That's what I got when I worked it out. It doesn't much matter what it is. I'm just trying to, the only point I'm trying to make is it's a polynomial. It's a way of trading in your old power and getting a polynomial. Now, but it has a beautiful property. This thing is called the Wick power. So phi to the p at A with this colons around it is called the pth Wick power of phi. And you'll see why in a moment. So here's a little lemma. D mu c, let's take the case where let P and Q be monomials of different degree. Then d mu c Wick ordered P, Wick ordered Q. Don't pay any attention to the fact that I'm calling it ordered, because that comes from quantum mechanics, and I know we're supposed to be doing quantum mechanics here, but we're not.
I was going to ask this question, since the notation is the one used in physics for normal
Yeah.
ordering.
And
Is this a relation
it's the same.
to a quantum field theory?
Yeah, it is. It is. The terminology comes from the fact that if you start with quantum field theory, where you encounter all of these things for an operator in an operator formalism, where you're putting the annihilation and creation operators in normal order for harmonic oscillators, then if you then go to the Euclidean world, where all of those operator formalisms for some reason turn into probability, you find yourself doing this. So, but it's hard to explain exactly why in a short time. So d mu c normal ordered P, normal ordered Q, it's just a polynomial, and P has just a polynomial and another polynomial, is always 0. It's an orthogonality condition. Basically something like, it automatically does something like Graham-Schmidt orthogonalization on the P and the Q. And I'm going to prove this to you because it's kind of cute. If I can find my eraser. Perhaps before I prove it, I should just summarize a couple of things that you learn from this. I'll do the proof at the end. Well, one part you learn from the proof, so I shan't tell you that. But I can explain right now why it's called a Wick power. Let's consider what happens if you do the derivative with respect to phi a of phi a to the p. So phi a to the p is this thing acting on phi a, just like I did it here. But this derivative is going to commute past that, right? Because they're just like other derivatives. So if you commute it past, you will do the it's basically saying you can put the d by d phi inside the colons, and then you will get p phi to the p minus 1a, like that. So it behaves exactly like an ordinary power under taking derivatives. That would remind you of Hermite polynomials. Hermite polynomials don't exactly behave like an ordinary power. There's some other normalization factor in, but they do have a recursion relation like this. And this should remind you of Hermite polynomials. If, in fact, we apply this recipe to a one-dimensional lattice, so if we take lambda just to be a one-point lattice, then the Gaussian measure, it becomes a kind of standard Gaussian measure, e to the minus 1/2 phi squared d phi. And what we're saying is that these are orthogonal polynomials. Now, orthogonal polynomials for a Gaussian, up to various factors that I can never remember, have got to be the Hermite polynomials, because they're uniquely determined by Graham-Schmidt up to normalization. And the normalization in this case is that these are monic. They always lead off with phi to the p, which is different from the Hermite polynomial normalization. But this is much more convenient for Feynman graphs, because now I want to show you what the significance of these things are in Feynman graphs. And to do that, it's best if I actually prove this lemma, because then we can see how to deduce their significance. So let's do the proof of the lemma. This is the proof of the lemma. So d mu, C, Wick ordered P, Wick ordered Q. We use Wick's theorem, which is still up on the blackboard there. It's e to the 1/2 Laplacian. And I'm going to drop this thing called C here, because I think it'll get in the way of my notation. Actually, if you don't mind, I'll just back off a second, and yeah, let's write it this way: P Q, and then we have to set phi equal to 0 at the end. So let's just think a little bit about the exponential of the Laplacian acting on a product of two things. It's a nice way to organize how to calculate this out. E to the 1/2 Laplacian acting on just AB. This is going to be A and this is going to be B. Now, inside here we have a d by d phi, actually lots of them, but I want to break them up. This is Leibniz's rule written in a neat way, explained in the Feynman physics lectures, but you can write d by d phi as a derivative which is condemned only to act on the A part, plus a derivative that's condemned only to act on the B part. What are we really doing? What I'm saying is, just temporarily, regard the fields phi inside A as being new variables phi sub A, and the ones inside B as new variables phi sub B, independent of the other ones. Do some derivatives according to this recipe, and then set phi A equal to phi B at the end. And if you, that's just a very good way of mechanizing the, what is it, the chain rule or some Leibniz rule in calculus, to do it that way. So if you split each d by d phi, which is inside this Laplacian here, into an A part and a B part, you'll get 4 terms. there'll be an AA term, there'll be an AB term, cross term, and there'll be a BB term, and some of them have halves and some of them don't. You get this one twice because there's a cross term between here and here happening in two different ways, because you have to split this d by d phi into a phi a and a phi b, and this one into a phi a and phi b, and then there's two cross terms. Now, at this point, all of these operators commute because they're differentiations with respect to different variables. And so you can write it as e to the Laplacian AB, this cross term part, acting on e to the 1/2 Laplacian AA acting on A, e to the 1/2 Laplacian BB acting on B. And then we have to set phi equal to 0 at the end. Now, the punchline is here, because how did we define, I mean, this is my A here, it's Wick-ordered polynomial P, right? And what is the Wick-ordered polynomial P? It's an e to the minus a Laplacian. I dropped the c, which means it's going to exactly cancel this out. So when I put in what the A and the B are, this is e to the Laplacian AB PQ. Yes? No? Everybody looks very suspicious. The e to the minus Laplacian, e to the plus Laplacian cancel out. This is the original P and Q without any Wick ordering. Now, what do we know about them? They are monomials of different degree. So this is going to have a very hard time giving any contribution whatsoever, because when Laplacian AB acts on it, it has to differentiate that as often as it differentiates this one. So what's going to happen is it's going to run out of things to differentiate either on the A or on the B. And it's going to give you 0, because you're going to set phi equal to 0 at the end. So the only term which other terms will have either phi's in them. So you just get 0. Now, that's the proof of this lemma, but it also tells you something else about the Feynman diagrams. Let's go back to these Feynman diagrams for a moment. Have I rubbed them out? That would be very sad. I guess I did. Okay. Squeeze it in here. Let's take a look at this one. Now, we already know by this lemma that I shouldn't take this to be a different degree than that, because otherwise I'll get 0. If you apply this e to the Laplacian formula to this thing, again, a certain part of the Laplacian, just this step where I went from where this thing, which was Wick-ordered P, got converted back into a P by this, that corresponds to the fact that you cannot have any diagrams with tadpoles in them here. See, normally, if you just ignore the Wick ordering for a second, I would have drawn this kind of a diagram. That would be one of them. And this one. But these ones are the e to the 1/2 Laplacian AA parts of the Laplacian, where a Laplacian acts entirely on that. And these ones likewise. And you can never have those if you've used the Wick ordering to cancel them out. So you'll never get these tadpoles. You will only get these diagrams here when you work out the moments of Gaussian the Wick-ordered moments of Gaussian integrals. So that's where I want to stop. I guess that's where I should stop, right? And now you're supposed to bombard me with questions for 15 minutes, so you have a hard problem.
So let's thank David first. David finished in his 75 minutes because we were very quiet.
Yes, you were.
But let me tell you, I think I know what the reason was. The exposition was very clear and right to the point, and some of even I learned some new things and I understood them. So we could just go to lunch, but this is for the audience to decide. So.
Yes.
Yeah, there are some questions.
Good. Okay, that makes me feel reassured that there are some questions.
Let's start with Reimer's.
Oh,
Well,
okay.
maybe you could be a bit more explicit about the edge automorphisms in your Feynman diagram.
I can try. Okay, it would take a little while, but I can try. So let me use some of this A-B trickery a bit to illustrate it. So let's take a. There are some places where we could have vertices, and these are called letters like x and y, which are in lambda. And if I had a polynomial, let's say product over a in lambda phi to some power that depends on the a, like we don't want this Wick ordering anymore, like this. And I want to evaluate this kind of an expression. You could do it this way. It's e to the, you could introduce a, you could make manifest in the Laplacian this x and y that are in here. And it's got to act on this thing. So I'll put that here. Now, when you expand, see now what I can do is I can take this as a product down here, right? And so what that means is between any 2 points, depending on how far out you expand this exponential, you can have 1 line, 2 lines, 3 lines, 4 lines, and so on, right? But they are divided by this 1 over the factorial that you have when you expand the exponential, which means that they're indistinguishable in terms of how you're counting them. So that factor of 2 that I was talking about before, for example, was really that 1 over 2 factorial in front of the Laplacian that when you expand the exponential. Now, it's obviously going to be a bit more complicated if you have, well, for example, a diagram like this. Edge automorphisms for that, I guess, are you can exchange any of these. I mean, to be more explicit, you have to say what you really mean by a graph. A graph would, you know what an incidence matrix is for a graph? So an edge automorphism is a permutation of the columns or the rows. I can't remember which keeps the matrix unchanged. And so basically what you have to do, which I would not be well enough organized to do that right here in front of you, but we can talk about it afterwards, is you would have to write this as the sum over first edge labeled graphs, where every edge that you can get here has a label. And then you would have to rewrite that sum as a sum over equivalence classes of edge not labeled graphs and things inside them. And then you get this automorphism group inside. And I think that's the best I can do in a short time in describing it.
What's the second question? Or two more?
The very last line you have already erased.
Oh,
Why did the tadpoles disappear?
why what?
I haven't quite got the last point. Why does it term with two tadpoles disappear?
Oh, why do the tadpoles disappear? Right, let's talk about that then. So, so doing a Gaussian integral on, let's say, let's do phi to the fourth at A and B. You write e to the Laplacian, which has to act on there, plus a Laplacian, which has to act on there, plus a Laplacian, which has to join them, and these ones have a half in front of them. Right? Now, if I Wick order these things, so I want to do a different integral where they're Wick ordered, then when I substitute in what this is, with a minus sign, like that, then what will happen is that these parts will get cancelled out at the same time as you erase that. Does that make sense? That's the crucial point. If you buy that, then you're forced the rest of the way, because now I've lost the ability with a Laplacian to ever join a point to itself, because that's the diagonal part of the Laplacian.
It's reminiscent of what you expect from a normal ordered object.
Yeah.
There is some kind of cluster property, which the expectation of, so if you take the expectation of product, then the tadpoles are somehow factorizable. They're disconnected graphs, and the expectation of one factor, a normal order factor should be zero. Something like this is
So
going
so
on
it's the
here.
same as removal of the disconnected diagrams usually in field theory?
Yeah.
No, that's different. The removal,
Not
and I
exactly
think,
the
no,
same,
the
but
removal
there's
of the
some relation.
disconnected diagrams has to do with whether you're calculating the log or not.
Yes.
Yes, this is somewhat different.
So this is different.
Right.
So to what is it related in the standard procedures that we know?
Well, I guess the only way I know how to I mean, you're asking me how to relate it to the Wick ordering of A's and A stars, right? Okay. You know, I don't have a good answer to why exactly that is. Maybe Tom has a good one right away.
Or
But
you could just check it in
you can
one
check
dimension.
it, yeah. You
check
can
it in one dimension.
Right. If you just check it, but that's not really a very good answer. I mean, no. I mean, I think I could do it. I guess the point is this. I mean, when you put some A's and some B's, A stars, that's like this, you get a very similar combinatorial structure of pairings when you move the A's past the A stars, right? I mean, every time you move an A past the A star, you get a commutator. That's very analogous to a Laplacian acting on those two guys and joining them up by a line, which is what's happening in my combinatorics. It just happens that it's the same combinatorics. Working out a bunch of commutators, moving A's and past A stars, means you're summing over all pairings. You probably would buy this a little more if you saw the standard formula for evaluating a Gaussian, which is this. If you have a bunch of fields, the way probabilists would write this is a sum over pairings of products of covariances like this, if you've seen this formula. So it's a sum over all ways of pairing phi's with other phi's and putting in a covariance for each one of them. But on the other hand, if you think of these as operators which have C commutators and you move them past each other, you will also get sum of pairings.
Probably the easiest way to satisfy, just to realize A as X and A star as dy over dx, and probably then Hermite polynomials will naturally appear as in oscillator representation.
Yeah,
Probably it's related to this. At least in 1D, as Tom said.
yeah. I mean, if you like, I can prove it to you I can prove Rodriguez's formula for you. But that I don't know whether a calculation is really a revealing answer. To me, it would be more revealing to realize that the structure of pairings is the same as taking commutators.
Question back there. Wasn't there another? I had 3 questions. No? No further questions? All right, and we go to lunch. Please be back.